Hi everyone, in today's video we are going to examine another crypto system called Vigenère Cipher. In this video we are going to formally define what Vigenère Cipher is, and we're going to see an example, a detailed example of Vigenère Cipher. I'm going over the definition of Vigenère Cipher. Just keep in mind, it may look overwhelming at first, especially if this is your first time seeing this definition. But I'm hopeful when we go over the example at the end, it will make a lot more sense to you. Now, as for the definition of Vigenère Cipher, it is important to note that this crypto system is a block cipher, meaning that the plain text and ciphertext are both divided into blocks of text, and the size of each block is determined by the size of the key. So let's say the key has length L, then we divide either plain text for the purposes of encryption or ciphertext for the purpose of decryption into blocks of L, size L. So we denote the ciphertext by letter C, and plain text by letter P, and the key by letter K, and we denote each element of the block by C1 to CL for the ciphertext, P1 to PL for the plain text, and K1 to KL for the key. For the encryption, we can simply add the elements of the plain text to the elements of the key, elements by element, so element-wise addition mod 26. More specifically, the ith element of the ciphertext is given by the sum of ith element of the plain text plus the ith element of the key mod 26. And for decryption, we subtract this time the ciphertext from the key. And that's how we can get back our plain text. So the ith element of the plain text is given by the subtraction of the ith element of the ciphertext from the ith element of the key, where I is an integer between 1 to L. Again, this definition may look overwhelming or abstract if it is your first time, but hopefully just bear with me. As soon as we go over the example, I hope it will make a lot more sense. So for the example that I've considered for the Vigenère Cipher, I thought maybe it'd be nice if we think that, let's say we are working for a police department and we have a highly confidential secret that shouldn't be disclosed, and if it gets disclosed, maybe we put our life in danger, and we want to tell our colleagues in another town that we have a secret. And for the key, since we are working for a police department, we've chosen our key to be just police. So this is our setup. Our plain text is I have a secret, and our key is police. The plain text I have a secret is a string of 12 characters, and the key police has a length 6. So that means that we can divide the plain text into 2 blocks, each of size 6. So we populate our table by just simply adding each character in each cell. So I goes in the first cell, H goes for the second cell, and so on and so forth. And we do it for the second block as well. And we want to add our key to our plain text. The key is police, so we do it for the first block, and we use the same key for the second block as well. So in the next step, of encrypting a plain text using the Vigenère cipher, we need to associate each letter in English alphabet to a number in mod 26. In another video that I've made already in about Caesar cipher, I've already explained how we get that table and how can we use it. So this might be a recap for some of you. If this is your first time, I hope it becomes clear to you how we can use this table. So letter I, the first letter in our table, highlighted in the red circle, we want to associate a number in mod 26. We look at our table here and we see that number 8 is the number that corresponds to letter I. So we go ahead in our second table and populate it with number 8. We look at our second character, letter H, and we go back to our table. We see letter H corresponds to number 7. And again, we populate the second cell with number 7. We can do the same for the rest of the characters. If you want to, you can pause the video and think what numbers are gonna go to each cell. We can see letter A goes with 0, B goes with 21, and so on and so forth. And similarly, we repeat the same process for the word secret. So for example, letter S goes with 18, and we do it for the rest of the characters. And then we do the same process for the word police. So letter P goes with number 15, and we do it for every single character as well. We can just look up their values from this table, and we write these numbers twice for each block. We do it twice in this case because we have 2 blocks, but let's say we have n blocks, then we do this process n times. Now that we have transformed our plain text and our key to numbers in mod 26, our next step is to add these values element by element. So we look at our first entry in the second table, which is number 8, and below that we see number 15. And simply we ask ourselves, what is 8 plus 15? Well, that's 23, and we denote it in the table below it. Similarly, we do it for 7 and 14. 7 plus 14 is 21. We do the same process for every single element in each block and each cell. So 0 plus 11 is 11, 8 plus 21 is 29, so on and so forth. So that takes care of the first block, and we do the same process for the second block as well, and we get these values. So we are pretty much done with the encryption component of the Vigenère cipher. We have a sequence of numbers that are supposed to correspond to letters in English alphabet, and that would be our ciphertext. So for example, number 23 corresponds to letter X, and we'll get that we'll get to this in a minute. And number 21 corresponds to letter B, for example. But there are also some values like number 29 or number 33 that actually do not correspond or like do not exist in this table. And that's fine because we are doing modular arithmetic. Again, I'm hoping that you're familiar with modular arithmetic. If not, please let me know in the comments, and I may make a separate video for a quick guide to modular arithmetic. But we are interested in these values mod 26. So we simply ask ourselves, what happens if we divide this value by 26, what do we get as the remainder? And that would be the value that we are interested in. So starting from 23, we ask ourselves, what is the value of the remainder when we divide it by 26? The answer is 23 again, because it's between 0 to 25. We don't need to do anything. Similarly, 21 and 11, same idea. But now number 29. 29 is greater than 25, which is the highest value that we have in this table, which is fine. But then we ask ourselves, okay, if I divide 29 by 26, what do I get as the remainder? The answer is 3. And the same idea applies to 6 and 4. Again, dividing 6 by 26, and you'll get 6 as your remainder, and same idea for 4. Now, number 33 again has a value that doesn't exist in this table, but we ask ourselves, when we divide 33 by 26, what do we get as our remainder? The answer is simply 7. And we do the same process for the remaining numbers in the table, and we note that all these values are between 0 to 25, so there's nothing special about them, and we just write them down again in this table one more time. Now we are almost done finding our ciphertext, and that would finish off things with the encryption component of the Vigenère cipher. The last part, we need to ask ourselves, what do these numbers correspond to in English alphabet using this table? So we ask ourselves, what does number 23 correspond to in English alphabet using this table? Well, the answer is letter X, and we write it down in this table. And this same process goes for 21 and 11. They correspond to letters V and L. And again, number 3 corresponds to letter D. And we write it down in this table one more time. 6 and 4, same idea. Number 7 corresponds to letter H. Again, we populate the cell with letter H. And we do the same process for the remaining numbers to find their corresponding English letters, and we get these values, and there we have it. At this point, we have encrypted our plain text. I have a secret with the key police using the Vigenère cipher to get this text, which supposedly doesn't mean anything to humans, and we can communicate securely, hopefully, with whoever we want, as long as we agree on a key. And in the next section, we can go over how we can decrypt this. But before getting there, we'll just have a quick recap of what we've done so far. So just a quick recap up to this point. We've started with a plain text. I have a secret. We divided into 2 blocks. We use the key police and added the word police to the secret, did some mathematical operations, and we got the ciphertext that you see down below, which looks pretty much nonsense. Now in the next part, we'll see how we can use the ciphertext and the same key police to decrypt this ciphertext and get back our plain text, I have a secret, one more time. So now we are starting our decrypting process of the Vigenère cipher. We have a ciphertext, we have the same key police. This time I'll go a little bit faster because it uses the same idea for encryption with a minor change this time, and we'll get to that in a second. But for now, we populate our tables with the elements of the cipher text divided in 2 blocks as before, and we add our keys in the table as well, the word police. So again, the same way that for encryption we looked up the value from the table to see what numbers they correspond to, we use the same process one more time for decryption. So we look at our ciphertext, we ask ourselves what does letter X correspond to in the table. It's number 23. We write it down, same idea for V, number 21, and so on and so forth. Again, as you may wish, you can pause the video and try to go ahead and find those values for yourselves. But I hope you get these values, and the same idea for the key police. Actually, these values are the exact same values that we use for encryption. So I refer to the word police actually because the values for our ciphertext is different from our plain text, but the key police, they have the same value as before, but for the purpose of demonstration we'll write them down again one more time here. So in the next step of decryption, and this is the step where decryption and encryption differ in Vigenère Cipher, we subtract the values of each cell. But it's important to understand why we subtract, and for the decryption component, and why did we use addition in the encryption component. The reason why is because Vigenère Cipher is an instance of a symmetric crypto system. So that means that if we encrypt a certain plain text using a key, we have to be able to recover the same plain text using the encrypted ciphertext and the key. So you can think of it as an inverse operation. So if you are able to use plain text and a key to get a ciphertext, there has to be an inverse operation to get us back to the plain text. So in a sense, the inverse of addition is subtraction. So it actually makes sense why here we're subtracting, and for encryption we were adding the elements. And just to complete this section, we ask ourselves, what is 23 minus 15? The answer is simply 8. And same process for 21 and 14, 7, and 11 minus 11 is 0. Now the next cell we have 3, and we are subtracting 8 from it, and that actually gives us a negative value, negative 5. We actually don't put plus 5, we record negative 5 and write it down in the table, and that's totally fine because we are interested in those values in mod 26, which is going to be our next step. And then we do the same process for 6 minus 2, which is 4, and 4 minus 4 is 0. Now again, we go to the first entry or first cell of the second block, and we have to do the operation of 7 minus 15, which is again actually negative 8. That's totally fine again, as we are going to look at those numbers in mod 26, they will correspond later to something, some positive value between 0 to 25. And then we can fill the remaining cells as usual. 18 minus 14 is 4, 13 minus 11 is 2, and so on and so forth, and we get these values. And now in the next section, we'll look at these values in mod 26 and try to look up their corresponding English alphabet from the table. So in this step, which is the exact same step that we did in the encryption component, we look at the values in our table in mod 26. So the values that are actually between 0 to 25, we can just write them as they are. in our new table. So 8, we ask ourselves what is 8 mod 26, or what is the remainder of 8 when it's divided by 26? Well, the answer is simply 8. Same for 7 and 0. Now the next value is -5, and when we divide -5 by 26, the remainder is actually number 21. The way I do it in my head, I usually ask myself what is 26 minus 5. That's a hacky way of doing it, but if you know other shortcuts, please let me know in the comment section. But we do going back to this table, we do the same process for the remaining values, 4 and 0. We just write them as they are. And then we go to the first cell of the second block, again, -8, 26 minus 8. Again, this is a hacky way. This is not a rigorous way of doing it, but that gives you the right answer, and that's 18. And again, 4, 2, 17, 4, and 19, we can just write them as they are. And now, the last step, we just need to look up what English letters do these numbers correspond to in the table that we got. So, for example, number 8 in the table corresponds to letter I. So we write I in the table. Same for numbers 7 and 0. 7 corresponds to letter H, and 0 corresponds to letter A. And then letter 21, as another example, corresponds to letter V. And we do the same for 4 and 0. So we get the same first block as the original plain text that we got. Hopefully the same happens for the second block. Let's check that out. Number 18 corresponds to the letter S in this table, so we write it down. Same thing for 4, 2, 17, 4, and 19. We look up their corresponding English characters, and we fill in the rest of the table, and we see we got the same plain text that we began with, which is what was expected. If we didn't get the same plain text, that was something to worry about, and that meant something must have gone wrong in the process. So we can see we get the same plain text. I have a secret as before. Before finishing off this video, I'm just gonna give you a quick recap of what we've done in the second component, in the decryption component, and have my closing remarks. So to give you a recap of what we've done in the decryption component, we started with the ciphertext. You can see it as a string that is pretty much nonsense. And this ciphertext was found using the plaintext and the key. So we used the key this time to find the plaintext and decrypt the message, actually. The main difference between plaintext and between encryption and decryption in Vigenère Cipher is the fact that during encryption we are adding the key to the plaintext. However, in decryption we are subtracting the key from the ciphertext this time around, and we were able to get back the same plaintext that we started with originally. Please note this video will also be accompanied by a Pythonic implementation of Vigenère Cipher, and I hope you'll find that one helpful as well. Also, you might have noticed that I kind of cheated in this video and kind of made life a little bit easy for myself. The plaintext that I used had 12 characters in it, and the key had 6. So 6 divides 12, and that made the Vigenère Cipher, which is a block cipher, a little bit easier for me. So you might wonder what happens if the length of the key does not divide the length of the plain text. That's totally fine, and I'm just gonna add an additional video to address that question. There is a technique in cryptography called padding. You might be familiar with it, and I will go over more details in that video to address this question, but the simple solution to that problem would be to use padding. With this, we come to the end of this video. I hope you've enjoyed and learned something new. As always, I would appreciate to hear from you and hear your comments or if you have any feedback. Other than that, thanks for watching, and I hope to see you soon. Bye for now.